Now that we have an understanding of the idea that a molecule that has a stereogenic carbon can exist in one of two forms, and those forms are enantiomers, we can think about the physical and chemical properties of those two enantiomers. And it happens that almost all physical properties of enantiomers are identical. So, for example, if I drew the two enantiomers of carbone. So I'm drawing them here, right? These are the two enantiomers of carbone. And if I think about my priorities, I see that the, um, the propenyl group would get priority number one, and then the carbon that would be attached to the carbonyl would get priority number two, and then the carbon attached to the alkene would get priority number three, and therefore I have R carbone, and on the other side here I have S carbone, right? So those are two absolute configurations. Notice I find them based on um, the arrangement of the substituents around that tetrahedral carbon. Now, in terms of physical properties, what do we typically look at? We typically look at boiling point, we look at density, we look at refractive indices. If I compare R carbone to S carbone, the boiling point of the two is identical. 227 to 230 degrees Celsius. Very high boiling point. They're both oils, but that physical property is identical. I can't distinguish between the two of them. Now, likewise, I can think about the refractive indices. So the refractive index of R carbone is 1.4990, and that of S carbone is 1.4970. Now, these are so close that we really can't distinguish between the two of them. Also, their densities are very similar, 0.959 to 0.965. Again, within a standard deviation, they are pretty much the same. So there's really no way, in terms of our the typical physical properties that we look at, to distinguish between R carbone and S carbone. It happens that there is really one main way that you can differentiate them, right? They differ physically in the way that they rotate plane polarized light. Now, this is kind of an abstract physical property, but it is a property nonetheless, and this is the way that we can distinguish between the two enantiomers of one another. What is plane polarized light? Well, I'll show you a diagram in just a little bit, but the idea that a molecule rotates plane polarized light is called optical activity, right? So if if a solution rotates plane polarized light, then it says it's called an optically active solution. What is plane polarized light? Well, here is a diagram that kind of demonstrates that. Obviously, light we can think of as a wave, right? We can think of light as a particle or a wave. In this case, we're thinking of it as a wave. And that wave is traveling in all different directions. We say it's unpolarized. If I pass that light through a prism, in which is called a Nicol prism, in which there are basically little filters that orient the light such that only light in one direction can pass through. Now I have plane polarized light. So light in only one direction is traveling through that prism. This is basically the way polarized sunglasses work. Polarized sunglasses are lenses in which you have Nicol prisms built into them. So they polarize the light such that light from only one direction comes out. They're basically filtering out light that is reflected off of the surface of of any surface, basically, right? So what happens is now this plane polarized light can pass through a sample. And if that sample contains a chiral molecule, that chiral molecule is then going to rotate the direction of that plane polarized light, such that when the light comes out of the tube, it is emerged at a different rotation, and we can detect that particular rotation. Now, one stereoisomer, it happens, will rotate that light clockwise, and we call that dextrorotatory. Dextrorotatory. And the abbreviations we use, there's really two types of abbreviations. One in which biochemists and molecular biologists use, and one in which organic chemists use. And that is D for dextrorotatory. This is what molecular biologists and biochemists use when talking about a lot of sugars. So you hear D-glucose. But organic chemists don't use D. We use plus. Plus is rotation to the of light clockwise, and then of course the enantiomer of the isomer rotates that light in the exact opposite direction and magnitude. So that's important to understand that both the direction and the magnitude of that rotation are exact opposites, right? So the magnitude's the same, but the direction is opposite, and we call that levorotatory. And of course, biochemists have the designation of L. We have the designation of minus. So anything that rotates it counterclockwise is minus. Clockwise is plus. Counterclockwise is minus. Now, oftentimes students get confused between RS, absolute configuration, and this is called the specific rotation, right? So enantiomers, each enantiomer has its own specific rotation. There is no connection between RS, the way that we're the direction of the substituents is, and plus minus the way that light is being rotated. We're using the same kind of terminology in terms of clockwise versus counterclockwise, but in absolute configuration, we're looking at the orientation of the substituents themselves, and with optical activity, you're looking at a physical property that you have to measure. There's no way to determine whether or not an enantiomer is plus or minus without physically going in and measuring its optical activity. Now, one thing to note is, key is that plus or minus, right, the optical rotation has to be measured. The other terminology that you need to understand is that there are oftentimes cases in which you have a 50-50 mixture of the two enantiomers. So you have 50% of one and 50% of another. In this case, we call it a racemic mixture. And if we think about the optical activity of that solution, so one enantiomer rotates it one direction, the other rotates it in the opposite, complete opposite direction with the same magnitude, and so they're going to basically offset one another, and therefore the entire solution itself is optically inactive. Now this can be kind of confusing. You can have a solution that contains chiral molecules, but that solution is optically inactive because they are a racemic mixture. So that's the only really time you have a solution with that's optically inactive is when you have a racemic mixture, which is a mixture of two enantiomers that's 50-50 mixture. We'll get into other types of stereoisomers so a 50-50 mixture of stereoisomers isn't called a racemic mixture. It's very specific. 50-50 mixture of two enantiomers of one another. That's the specificity that you have to understand. So if we go back to, drawing our structures of the two enantiomers of carvone, right? R carvone and S carvone, and we think about the physical properties, we see, okay, we can't we can't distinguish the two of them between any of the normal physical properties, boiling point, density, refractive indices, but now we can distinguish in the optical rotation called the specific rotation. And we find that, our carvone rotates it to plane polarized light to the left. And it has a particular specific rotation that you don't really need to know how to calculate specific rotation of solutions. I'll never ask you anything like that, but you do need to recognize that if I had a solution that only contained R carvone, it would rotate it and it would be optically active, right? If I had a solution only of R carvone, that solution would be optically active. Would you know that it rotated it to the left? You wouldn't. I would have to give you that information. And so it simply happens that the S enantiomer rotates it then to the right. If I know one, I know the other is the opposite of it. So we can then, and oftentimes you'll see a compound that is a particular enantiomer with a physical property of minus or plus. So this tells you that it's giving you the specific rotation, the direction of the specific rotation. So R carvone, we can now add the minus R hyphen minus hyphen carvone. And likewise, we can say S hyphen plus hyphen carvone. So that minus and plus is a physical property of that particular enantiomer. Again, I can't stress enough, it is a physical property. You have to measure it. There's no way you can determine that on your own. But the R and the S absolute configurations you certainly can determine on your own. Now, let's think about the chemical properties of the two enantiomers. And really, for the time being, the only thing that you need to know about chiral molecules is that when they react with achiral molecules in their environment, they react the same way. So two enantiomers, I have two enantiomers, and both of them are reacting with some achiral molecule. The result is going to be the same. The big difference is that when you have two enantiomers reacting with other chiral molecules, the results can be very different. So if I look, if I think about the two enantiomers of carvone, plus carvone and minus carvone, one is spearmint, the other is caraway seed oil. Why do we see a difference? Well, what's happening is at the molecular level, both of these enantiomers react with chiral taste bud receptors on your tongue. And when they do so, they send different signals to the brain. So they're reacting differently when they come into contact with a chiral molecule. It happens that taste bud receptors are chiral, and therefore we can distinguish between two enantiomers simply based on the receptors and the signal they send to our brain, which is kind of cool.